Okay, we're gonna get started here. I have water boiling, so there will be tea time. I think what we're gonna start off with is, well, I should do a volume check. Okay. Okay. I'm gonna go backtrack and we're gonna take a look at problem 2 again, just from the top. First question here is, of course, to compute the least squares regression line. And if you're given data, remember there are two different ways that we can access this question. The first way is with a computer printout. Typically, those computer printouts will be missing some parts that you will have to fill out. But the other way to do it is using just a table of values. And that second way is what we have here. The economist who wants to study the relationship between disposable income and the money that a family spends on food every year. Random sample of 8 families, we have some data. And the first thing we're going to do with this is, of course, we're going to put our alleged explanatory variable in L1 and our alleged response variable in L2. Can't do anything without that. Okay, from there, we're going to use the function linreg a plus bx. Make sure you're doing a plus bx. There are 2 linear regressions that your calculator can calculate. One of them is for stats, one of them is for algebra. You, of course, are in statistics. So that's a good-looking window. Notice that my L1 here is the X list. My L2 here is the Y list. We're going to get an output looks like this. You generally want to keep 3 or 4 significant figures. That should be fine. So we're looking at the food budget is 10.28 plus 1.31 times the income. I'm not going to fuss too much with the units, but you should know that the units here are different for each one. So food budget, I believe, is in hundreds, while income is in thousands of dollars. Letter B, we're supposed to determine whether or not yearly income is a useful predictor. And if it is a useful predictor, what would be the appropriate set of hypotheses? Okay. So first thing is we're going to be using beta, really. So we should figure out what beta stands for. And of course it is the slope of a line. We want to put some context in here, so we're going to say it's the increase in yearly food expenditure for every increase of $1,000 in yearly income. Maybe I should write it like that, for every $1,000 in yearly income. Someone in English said that if the numbers are less than 10, you're supposed to actually write them out. Is that the rule of thumb? Less than 10.
Every English teacher changes it. Like something like, oh, if it's less than 50, if it's less than 20. So.
Less than 50?
Yeah, so do whatever.
Less than 10 is good enough. I don't know. You probably could have used the Arabic number 1, and I would have been fine with that too. Anyways, appropriate if you want to know if the linear regression is useful. That means you're looking at a model utility test. Model utility is beta equals 0 versus beta is not equal to 0. Alternative hypothesis here, beta is not equal to 0. If you conclude the alternative is true, that means you're saying the linear regression is useful. So rejection's a good thing, which is funny because prom's coming up. So. Zing. Letter C. Some assumptions that must be checked for the t-test. Are the assumptions met in this problem? There's only two that I want you to worry about. The first one, of course, is the shape of the scatter plot needs to be linear. And number two, the residuals for any particular value of x should be approximately normal. So residuals are approximately normal. Those are our two conditions. Let's check them. Condition 1, we've gone ahead and we've created the scatter plot. I don't know if you need me to go over that or not. Scatter plot, we're simply going to go, let me make sure my data is here. I don't even remember if I have the data here still. Is that right?
Yeah.
Okay, so the data is there from any screen. I'm going to pick the home screen though. I'm going to go to stat plot, so second F1. And we're going to look at that first plot. We'll turn it on. Remember, reading from left to right, we have scatter plot, connected scatter plot, histogram, modified box plot, or box plot with outliers, normal probability plot. We want, of course, the scatter plot. Quick visual verification. Is a X list in L1? Yes. Is a Y list in L2? Yes. And from here, we'll zoom. And we're going to zoom stat. So zoom 9. Boom. And does that look linear? Yeah. This point right here kills the linearity, of course. It's kind of far away from the rest of the trend. What? What? Calculus. Calculus. It's calculus. There we go. Okay. Yeah, at this point may look like it kills a relationship, but let's just see. Are the points increasing as is the y coordinate increasing as the x coordinate increases? Generally speaking, yes. We do see a diagonal pattern here. Not a very strong diagonal pattern, but there is a diagonal pattern. With or without this point, that diagonal pattern exists. Does it look linear? That might be debatable, but it does look like we have an upward thing. I'm going to say approximately linear is okay here. Okay? Okay, so it looks approximately linear. The second condition you can never actually test. Okay? We can assume that we'll have to assume that the residuals will be approximately normal, but there's no way for us to actually look. Okay. And that's that. Letter D. We're going to use the lin-reg t-test on the calculator to test the hypotheses in part B. So this should be good for everybody's calculator here. Let's just do this live. We'll go to the calculator. From the home screen, we're going to go to that really powerful menu, Stat Tests. I'm going to go the long way down. We're going to look for linear regression t-test. There it is, linreg t-test. Linreg t-test. Go ahead and push enter. We'll get to this screen. Do we have the X list in L1? Yes. Do we have the Y list in L2? Yes. Is this our appropriate alternative hypothesis? Yes, it is. Let's make sure. Yeah, that's my alternative hypothesis. Beta is not equal to 0. All right. Once you have that all out of the way, you're going to calculate it. There we go. We have a T star of 2.75. We have a p-value of 0.334. 6 degrees of freedom. We already know the values of A and B. That S is SE. And of course, you know what R and R squared are. But really, if you're using the linear regression t-test, you don't particularly need to read much past the degree of freedom.
So for what's SE?
Standard error, the standard error of the residuals. Okay, and let's see. Great. T star is 2.75. Notice I have this written out here. The p-value is equal to 2 times the probability that T star is greater than 2.75. That gives me a p-value of 0.0334. I didn't have to calculate it. Calculator did it automatically, and I'm good with that. Part E, appropriate conclusion for this at a 5% significance level. So we have, since the p-value 0.0334 is less than alpha 0.05, we're going to reject the null hypothesis. If the null hypothesis was true, the probability of obtaining our sample would be about 3%, which is unlikely. Since this is unlikely, we conclude that beta is not 0. And the linear regression is a useful model. It may not be the correct model, but it's a useful model. It's pretty much the same conclusion we've been writing in class all semester.
Would we say that's useful also?
Yeah, that's the little bit extra right there. And I think it's tea time. I'll be back in a minute. You guys are going to be 18. You're going to be old enough to vote in the next election. When's the cutoff, do you think, for voting? Okay. Any other questions with either problem 1 or problem 2? Yeah. Let me see the conclusion I gave you. This is a couple of years old. P-value is less than alpha. We reject null hypothesis. Conclude that linear. No, I don't like that one. Okay. I don't like that. Okay, if that's the case, let's go on to question 5. A t-test on the value of beta and a regression line is to be performed. In order to satisfy the conditions for the test, number 5, what would be the ideal shape of the scatter plot of the data? Yeah, the scatter plot of the data should be approximately linear. Shouldn't be surprising, that answer. Everything we're doing here is for things to be linear. What should the residual plot look like? Of course, residual plots should not have a pattern, right? Residual plot should not show clear pattern. Okay. 7.
How do we create a residual plot?
You plot the x coordinates in L1 versus the residual list.
Oh, okay.
What does a fan shape indicate? Okay, a fan shape well, basically that means that the linear relationship is stronger for one part of the data than the other part of the data. Okay. Indicates the regression line works better or is a better fit for only part of the data. That'd be the skinny side of the fan. Okay. (18) Describe the ideal shape of the histogram for the residuals. We're not really going to talk about this one, so we can skip this. Okay. Well, but just so between you and me, the histogram of the residuals should not deviate significantly from normality. Remember that phrase, deviating from normality? Number 9, how many degrees of freedom? That's going to be equal to the number of coordinates. minus 1. No, minus 2. What am I doing? Okay. 10. We have this chart, so we're just going to go ahead and do this live. Let's see, we want that data in our calculator. Let's take a minute to do that. Oh, I'm in the wrong place. It'd help if I checked I was in L1. Takes care of that. So 10, what is the equation of that regression line? Should probably screenshot this also. Let's get the next screen, of course, is going to be calculation of a linear regression A plus BX. Hmm?
So for number 10, you can write that we can use lim reg A plus BX.
You don't have to write it. I'm going to assume you're going to do it. There we go.
This one we can just put y equals to that, right? Since there's nothing.
Yes, since there's no context, it would be okay. So what do we got? Y hat is equal to 81.644 minus 2.491 x. B, let's get a confidence interval. Does everyone have does anyone have an 83? You're going to look for a program called BINT.
Bent.
B interval. There you go. Okay, let's take a look at this screenshot. We're going to be looking at a program. No. Stat. Test. I'm going to take the short way around here. I'm going to go to a lin reg t interval. T interval, right? Yeah, t interval.
Why not t-test? Because it really comes. Okay.
No, but we used inverse T program in class to find two critical.
Oh. Yeah, but we don't have a way of finding S.
Oh.
SB. Okay, we have L1, L2, frequency level, confidence level. Do I have the right confidence level? Yeah. And then we're going to calculate. calculate that? That's great. Okay, so we say that B is in, oops. Oh wait, no, that's not what I want to do. I want to do that program, right? There we go. Let's take a screenshot of that. I kind of like the one I programmed better. But that's just me. So what do we have? Beta should be between negative 3.733 and negative 1.249, bless you. Okay.
Mr. President, can you go for what we'd have to write if it was, if they wanted us to write everything out? Or we don't really need to do that?
You would have to get the margin of error.
Okay.
And the margin of error is going to be equal to T critical times SB.
We don't have SB.
SB usually would be given from a chart. SB is found on a chart.
And would we need to satisfy the same conditions for the p-test?
Yeah. And then we're going to say beta. That's going to be equal to B plus or minus margin of error.
So with this program, that's what I need to do, right?
Yeah. That program, I think it gives you the margin of error, doesn't it?
Yeah. It gives you the margin of error and SB.
So you'd have to do the adding and subtracting on your own. That's why I like that program. SB is given. It shows you SB.
Should give it to all of us then.
Well, she can't do an interval any other way. I can give it to you if you want it. Any questions on that for beta? Okay, let's go on to question 12. So we need to find test statistic, degree of freedom, p-value for the set of hypotheses. And we can get all of those cleanly by using the t-test on the calculator. So we're going to stat, test, and now we're going to linear regression t-test. That everything looks perfect the way it is here. Oops. Take a linear regression t-test. Let's calculate now. Should be everything I need. Right there in that one screen. So let's see. What do we have? We have, first of all, test statistic. T star equals negative 5.57. Next, degrees of freedom. Equals 4. Okay.
Is the 4 subtracted from the x values? Like, I get that it's 6 minus 4 is from the x values or y values?
Both.
But
You
if they were
should,
different,
then it would never be. P-value. That's going to be equal to the probability that t is greater than nope, 2 times the probability that t is greater than 5.57. Notice I make that test statistic positive. And I double it.
Is it supposed to make T star or is that a different thing?
Yeah, well, no, t is fine. And that's going to be equal to 0.0051. That should be everything, right? We have the test statistic, we have the degree of freedom, we have a p-value. Any questions? Brett?
you will email this.
Yeah, this is emailed.
For the one about fan shape, are there other shapes you have to know also?
Fan shape is one of the ones that are really specific. You should just be careful of any time it shows a structured pattern. That typically means that the linear regression is probably not a good choice. Okay, I'm going to stop the recording here.